The interstellar comet known as 3I/Atlas has recently become the focus of intense scientific interest as astronomers continue to uncover surprising details about its behavior while traveling through our solar system. Although the comet and its long veil of dust remain unreachable for any Earth-built spacecraft, researchers have found that this unusual visitor from another star system is producing far more than just dust. According to new observations, 3I/Atlas is also generating a secondary, hidden trail made of charged particles, an ion tail, stretching behind it as it moves through the solar wind. This discovery has inspired a bold proposal from two European Space Agency scientists who now believe that humanity may have an unexpected chance to study this interstellar material up close. These scientists argue that the flight paths of NASA's Europa Clipper mission and ESA's Hera spacecraft will naturally align with the comet's ion trail in late 2025, allowing the two spacecraft to pass directly through the stream of particles left behind by 3I/Atlas. If this alignment occurs as predicted, it could offer astronomers an unprecedented opportunity, the chance to collect indirect samples of matter that originated outside our own solar system. The idea, presented in a new scientific paper by researchers Samuel Grant and Geraint Jones and published on the AR-14 preprint server, outlines how the geometry of the spacecraft trajectories may place both missions inside the ion tail for short but scientifically meaningful intervals. Grant and Jones explain that between October 30th and November 6th, 2025, NASA's Europa Clipper spacecraft may become immersed in the ion tail, opening a small observational window during which its instruments could detect the signatures of charged particles flowing outward from the interstellar comet. The researchers emphasize that such a moment, if it occurs, would be historic. Humanity has only observed two confirmed interstellar objects, Oumuamua and 2I/Borisov, before the discovery of 3I/Atlas. Neither of those earlier objects offered a practical way for spacecraft to sample or study their material directly. The possibility that two active missions may cross this new comet's ion tail by coincidence is extraordinary, and scientists describe the alignment as a rare gift of orbital mechanics. According to the authors of the study, the charged particles in 3I/Atlas's ion tail are not dangerous to the spacecraft. Ion tails form naturally when the sun's radiation ionizes gases released by a comet, and the solar wind then sweeps those ions into long, thin streams that can extend millions of miles. These streams are usually harmless to spacecraft, although they can reveal critical details about the composition of the comet and the nature of its interaction with surrounding magnetic fields. If Europa Clipper's sensors register fluctuations in the local solar wind, changes in magnetic orientation, or unusual particle signatures while passing through this region, scientists may be able to reconstruct the characteristics of the comet's ion environment. This would allow researchers to infer the chemical makeup of the ejected particles, giving them indirect trace samples of material forged around another star, material that has traveled for untold millions of years before reaching our solar system. Even more surprisingly, Europa Clipper may not be the only spacecraft with the chance to cross paths with 3I/Atlas's ion trail. Grant and Jones note that ESA's Hera spacecraft, heading toward the binary asteroid system Didymos and Dimorphos for post-impact studies, might encounter the ion trail earlier. Their calculations suggest that Hera may become immersed in the tail between October 25th and November 1st, 2025. Hera, designed to study the aftermath of NASA's DART mission and the physics of asteroid deflection, carries instruments capable of measuring plasma, charged particles, and electromagnetic activity. Because of this, the spacecraft might collect another set of valuable data regarding the interstellar visitor. With two spacecraft sampling the same ion tail at different times and in different regions, researchers could compare the readings to build a more complete profile of the structure, density, and evolution of 3I/Atlas's ion environment as it moves through the heliosphere. One of the key features scientists expect both spacecraft to observe is known as magnetic draping. This phenomenon occurs when the solar wind flows past the nucleus of a comet and the interstellar dust and gas interact with a magnetic field carried by the wind. When this magnetic field encounters an obstacle, in this case, the comet's coma and tail, the field lines begin to wrap or drape around the object, forming distinctive arc-like patterns. These draped magnetic fields can alter the solar wind flow, create pockets of enhanced charged particle density, and even produce shock-like structures. If Europa Clipper and Hera detect signs of magnetic draping while traveling through the ion trail, researchers could use this information to deduce key features about the physical size of the coma, the strength of the solar wind at the time, and the speed at which ions are being released. Such data would be invaluable for understanding not just 3I/Atlas itself, but the general behavior of interstellar comets interacting with a new stellar environment. For decades, astronomers have dreamed of the possibility of analyzing material from another planetary system. Meteorites found on Earth can carry ancient stardust and isotopic clues about nearby stellar explosions, but they do not represent intact samples from a modern, active interstellar object. Spacecraft missions like Rosetta and Deep Impact have given scientists direct measurements of cometary material from within our own solar system, but capturing even indirect evidence from a comet originating around another star would be immeasurably more significant. Such material could carry clues about chemical conditions in distant star-forming regions, reveal differences in organic molecules, or show variations in isotopes that could help astronomers compare the early solar system with other planetary nurseries. Although Europa Clipper and Hera are not equipped to capture solid particles or bring samples back to Earth, their ability to measure the behavior of charged particles, plasma fields, and solar wind interactions makes them surprisingly capable tools for gathering indirect but valuable data. What makes 3I/Atlas particularly intriguing is its unusual activity. Unlike 2I/Borisov, which behaved much like a typical comet, or Oumuamua, which displayed no tail and remains mysterious, 3I/Atlas demonstrates unexpectedly intense outgassing for an interstellar object. Its dust tail has already drawn attention for its brightness and structure, but the newly discovered ion tail adds a new layer of complexity. This suggests that the comet is interacting strongly with the solar wind and may be composed of volatile materials that respond differently to sunlight. The ion tail, invisible to optical telescopes, but detectable in ultraviolet or charged particle sensors, reveals that its nucleus is actively shedding ionized gases. If Hera or Europa Clipper confirms this through in situ measurements, researchers will gain critical information about the composition and reactivity of these gases. Although the spacecraft will not experience any danger while passing through the ion tail, the scientific implications of this event could be profound. The data collected could represent the first direct interaction between human technology and material from beyond the Sun's gravitational family. Even small readings, tiny fluctuations in the solar wind, slight changes in electromagnetic fields, or the detection of unusual ion species might revolutionize scientists' understanding of interstellar comets. Each interstellar object that enters our solar system carries the history of its home system encoded in its frozen ices and trapped dust grains. By analyzing the behavior of the ion tail, researchers can gain a window into those distant origins without needing a sample return mission, which would currently be technologically impossible. Researchers emphasize that this opportunity is largely accidental. Europa Clipper is on a mission to study Jupiter's icy moon Europa, searching for clues about its subsurface ocean and potential habitability. The spacecraft's flight path was designed to place it on a long, looping trajectory toward Jupiter, not to intercept cometary material. Hera, similarly, was never intended to sample interstellar debris. Its goal is to analyze the impact site where NASA's DART spacecraft successfully altered the orbit of the moonlet Dimorphos. The fact that both missions may pass through the ion trail of 3I/Atlas is the result of natural orbital alignment rather than deliberate planning. Had 3I/Atlas arrived a few years earlier or later, the opportunity would not exist. Scientists will now work to determine whether the instruments on both spacecraft can be properly configured to maximize data collection during the brief window of opportunity. Because neither mission was designed for this purpose, mission planners may need to adjust observation schedules or modify instrument settings to detect the faint ion signals. Even small preparation steps could increase the chances of capturing meaningful data. The scientific community is already discussing how the readings from both spacecraft could be combined to produce the first multi-point measurement of an interstellar comet's plasma environment. If successful, these spacecraft fly-throughs could deliver the first-ever observational dataset of its kind. Measurements of charged oxygen, carbon, or nitrogen ions, if detected, would allow scientists to compare interstellar comet composition with that of known solar system comets. Differences in isotopes, ionization rates, or magnetic field interactions could reveal how environments around other stars shape the formation of comets and planetary systems. This, in turn, could contribute to larger questions in astrophysics and planetary science, such as how common certain organic compounds are across the galaxy or whether planetary systems, like ours, share similar chemical building blocks. As 3I/Atlas continues its journey, it will eventually leave our solar system behind and return to the deep interstellar void for countless millennia. But the brief moment in which it crosses paths with two human-made spacecraft could leave a legacy far greater than the comet itself. For the first time in history, humanity may have the tools, the timing, and the scientific readiness to study material that originated around a distant star, material that has traveled unimaginable distances to find itself brushing against the sensors of two spacecraft built on Earth. This unexpected alignment offers a reminder that even in the vastness of space, chance encounters can provide extraordinary opportunities for scientific discovery.